The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and welcome to the Research Results webinar. My name is Mike Fitch with the Ohio LTAP Center here at ODOT, and we appreciate your participation. As we get started, please take a moment to locate the questions box in the GoToWebinar panel. During the presentation today, please use the questions box to send in any questions you might have. And also, please note we will discuss all questions at the end of the presentation. Looking at the handouts section of the GoToWebinar panel, please note also that a PDF copy of the presentation is available for reference. With that, we will go ahead and turn things over to Ryan. Hello.
Mike, thank you for that introduction. My name is Ryan Mahle, a research engineer here at the University of Cincinnati, working under the leadership of Dr. Munir Nazzal in the Center for Smart, Sustainable, and Resilient Infrastructure. I am so excited to have the opportunity to present the results of our STAR program, that stands for Student Transportation Advancement Research Program. And the title of this presentation is The Development of a Scaled, Connected, and Autonomous Vehicle System and a K-12 Educational Resources based on CAV in a Box. I'm grateful for the other members of our team that participated on this project with me, including Dimitri Menashra, Hakam Batania, Safa Suela, and Mahib Khan. I'd also like to certainly acknowledge the many individuals. I don't have time certainly to name them all, but would like to particularly thank the Ohio Department of Transportation and Drive Ohio for sponsoring this study. So with that, let me offer a brief outline of what we plan to do with our time here in the course of this presentation. I'll provide a brief introduction showcasing the background of how this project came to be, our research objectives, stating some of the goals of this project, our research approach, in which I'll walk through our work plan. I'm going to spend the most amount of our time going through the results and the lessons learned over the course of the last 18 months, and then we'll hit on some conclusions and important recommendations that were developed during the course of this study. I plan to offer at least 10 minutes for a question and answer period. And as Mike noted, please feel free to offer your questions in the comment box, and we'll make sure to reserve enough time to answer those, but at the end. Beginning with the introduction. So this project is really based upon a system that was developed by Leidos called CAV in a Box. CAV in a Box is a learning tool that is really catered towards technicians and an audience that's really on the order of maybe the undergraduate level, or a high school student that's pursuing some degree of technical knowledge, technical experience. This project is intended to complement that, to expand upon that. So CAV in the Box has been, from the beginning, our jumping off point. In fact, our inspiration. So the innovation of the pursuit approach in this project lies in both the audience and the application. We wanted to increase the number of applications that CAV in the Box was doing, but we really wanted to target our audience for a younger age group. So our research objectives, really our overarching goal, is to prepare and inspire middle and high school age students to be engineering leaders, informed decision makers, and active participants in tomorrow's technological revolution. I think every word in that sentence is valuable and important. What we learned from the outset is that whereas existing comparable resources, and by that I certainly mean CAVE in the box as well, they're somewhat limited with respect to audience and application. This project targeted a younger audience, aimed to excite the interest, encourage the potential of those younger students of diverse learning styles and backgrounds. So with this aim in mind, the performed research set out to develop an engaging curriculum with related activities and educational opportunities that were specific to that target audience of grades 5 through 12. Really hitting on connected and autonomous vehicles, smart infrastructure, the advantages and limitations of sensor technologies with respect to environmental conditions, and the model development or the model data development path of collection, processing, training, and testing. We want to develop a tool and associated activities, resources, learning opportunities to be able to teach these things to this younger audience. The supporting technical objectives of this study included, first and foremost, the development of a prototype for an age-appropriate, portable, interactive educational model based upon the logic of the existing connected and autonomous vehicle education, that is CAVE in a box tool. So again, that was our jumping off point. And from there, we wanted to build something that was new, that could demonstrate the functionality and applicability of CAVE technology and various data collection instrumentation. We really felt that this was on par with the learning opportunity that presented itself to grades 5 through 12. We also wanted to consider the integration and practical use of various sensor technologies. Certainly simple camera imaging was a good starting point for our scaled system, which I'll discuss quite extensively in a little bit, but also LiDAR, also GPS. So there was a lot of opportunities to be able to integrate, to discuss, to challenge our young learners in this way. We also wanted to create accompanying educational resources and learning opportunities for the developed CAVE system in collaboration with Ohio educators and correspond them to STEM learning objectives: curiosity, problem solving, communication, these big buzzwords in the world of STEM that have a lot of value. We wanted to take them seriously and to offer resources that really met the objectives not only of this project, but of educators across the state. We also, in the course of this project, aimed to develop and provide training for Ohio educators on the developed system, and certainly offer rallying events and mentorship opportunities, none more significant than our ENG2YOU Future Engineers Camp, which I'll highlight later on in this presentation. But also, going along with that, classroom demonstrations and outreach events in support of connected and autonomous vehicle education. The point that I really want to underline here is that we essentially built not only a learning tool, but around that, a collection of resources, and even around that, a collection of learning opportunities. We built a laboratory, which I'm really excited about. So more on that in just a short bit. So our research approach is identified in these 10 tasks. So, first of all, we identified grade-specific learning objectives. We'll talk more about that in a little bit. We explored the CAVE in a box system. We developed and evaluated a prototype of a scaled system that was specific to our target audience of grades 5 through 12. We developed learning activities and associated lesson plans along with that, as well as Task 5, supplemental resources. We aim to, in Task 6, empower Ohio educators via training throughout really every phase of this project. In Task 7, we hosted an engineering leaders training for undergraduate and graduate students here at UC. And then in task 8, a future engineers camp with, again, that target audience of grades 5 through 12. In task 9, we organized student outreach events that were very successful. We'll talk more about that briefly, shortly. And in task 10, we prepared and submitted a final summary report and fact sheet. So task 1, identify grade-specific learning objectives. How do we do this? So the first thing we needed to do is we needed to establish relationships with middle and high school students. We did not want this project to exist in a vacuum. We recognized that anything that we were going to do in the world of education needed the collaboration of high school faculty, middle school faculty, and administrators, particularly in those districts representing diverse or underrepresented population. We wanted something that would work. We wanted something that an educator actually found to be useful, to be aligned with Ohio learning standards, all of that. So in this way, educational needs of educators and their students would be better understood, and the practicality and age appropriateness of those educational tools, resources, opportunities could be developed in future phases and would be calibrated according to their initial inputs and later feedback. And so that collaboration from the outset was vital. We did that by creating a mailing list of over 500 educators, certainly highlighting Southwest Ohio, but really all throughout the state as well. Part of that outreach included a survey that was distributed to that mailing list, from which over 50 local and regional middle schools and high schools participated. So this survey was sent out in 2 phases. We had an excellent marketing campaign to really seek after their, to excite their interest, to seek after their participation and collaboration. The questions of the survey consisted of the information regarding the school, but also school demographics, the grades that were taught, the subjects that were taught, their use of STEM in the classroom, their use of technology in the classroom, their preferred resources, student engineering interests, educator familiarity with connected and autonomous vehicles. What priority standards did they believe were already aligned with what it is that we were trying to do? Their learning objectives and outcomes that they thought was most most appropriate to the resources that we intended to provide. The zone of proximal development, that is the gap, essentially between what a student can learn on their own and that knowledge that is just outside of their reach, by which they're able to achieve and master, through an educational resource or a teacher, right? So what is that gap that we can close in this project? And we also wanted to learn more about the educator interests and their level of participation further down the line in this project as well. So you can see here's a map of Southwest Ohio highlighting the number of schools and kind of the geographical layout of where our participants in this survey and in our STEM educator outreach lied. So a lot along that I-75 corridor. Based on the results of this survey and our conversations with these educators, we identified the following: priority standards, key learning objectives and outcomes, and age-specific zones of proximal development. This is something that we needed to know from the start. The most significant challenges that were identified by their educators: time. So if that was the case, we needed, to create resources that could be fit into an already busy testing schedule and learning schedule, right? These are things that we needed to think about. Resources and materials, and that's another way of saying costs. So we needed to recognize that we needed to keep our costs down in whatever tool resources we were going to invite them to participate in. And then student engagement, interest, ownership seem to be lacking all across the board. So whatever we were going to do, it needed to be hands-on, it needed to be exciting, it needed to be fun, it needed to feel like a game. All of that was important. So our top priority standards, so these are existing Ohio learning standards that we can align to really everything that we've constructed throughout the course of this project. And you kind of see, this inspire and motivate, all of our tools and resources. But number one was to make sense of problems and persevere in solving them. That being the case, we don't necessarily just share the answers to everything, that we have our students doing. We want them to really exercise their critical thinking skills. We want them to persevere in problems, to answer the questions themselves. And so they're absolutely, that is embedded in the resources that we created. We want to identify a problem and use an engineering design process to solve the problem. Even the nature of an engineering design process, be it kind of something like, the hypostatic method of identify the problem, or simply, just the data collection process, from processing to visualizing to cleaning your data to training to testing. Like entering into that process was an important part of the resources that we created. And then certainly demonstrate that solutions to complex problems require collaboration, interdisciplinary understanding, and systems thinking. So that is embedded in our resources and our tools as well. Everything that we do, the students are working in teams. Task 2, so if you recall, our task 2 was really to explore the existing cave-in-a-box system that was developed by Leidos. I won't touch on this too much, but we really wanted to have a firm understanding of what this system was able to do. This exploratory task included the evaluation of the appropriateness of the embedded technologies and current applications. So we could tell right away, limited with respect to applications, although it's an amazing tool, but also it's very expensive, as well. So it's certainly not going to be at a price point the average Ohio educator is going to be able to jump into, and it's a little bit more technical, a little bit more in depth than what the average middle school student is going to be able to handle. But where potential application or relevance to students and educators of grades 5 through 12 was discovered, the ingenuity of the existing cave-in-a-box tool was retained. So what did we see? We saw modularity. So we wanted our systems to be modular. We wanted those applications for which cave-in-a-box is known to be retained in our system as well. Task number 3. So in task number 3, we wanted to develop and evaluate a prototype of a scaled system. So again, inspired by that cave-in-a-box tool, we wanted something that was suitable for classroom learning for that middle and high school audience. This system serves as the flagship tool of this project, and it's really punctuated by its ability to capture the attention of its young users, and it advances, in one way or another, all the associated activities, all of the learning opportunities that go along with this project. It really is the centerpiece of the program that we developed. It's characterized by its accessibility to youth, the simplicity of its design, and the versatility of its applications. The scale system was designed to be also as realistic as possible to effectively explore the fundamental concepts of connected and autonomous vehicle technology, and as modular as possible to allow for modifications and tangential assignments appropriate to the age of the student user. So really it is a small, connected, and autonomous vehicle. That is what we have constructed. This is some of the parts and pieces of the early stages of our scaled cave system. And from there, in this task, we began that iterative process of hardware assembly and software installation, camera configuration, car calibration, data training, application creation. All of this took some time. With that, we're developing, a connected and autonomous vehicle, but also we were very interested in the associated infrastructure. So one of the elements that is really key to CAV in the box, from which this system is inspired, is kind of this two-part collaborative system of an infrastructure kit and a mobile kit. Well, certainly the car was going to serve as our mobile kit, but we also needed to have our infrastructure kit. And so we built one, according to those dimensions, one that was at a scale that would serve the purposes later on for our ENG2YOU Future Engineers summer camp. So here's just a few pictures highlighting the development of our scaled CAV system and the initial testing of our connected autonomous vehicle actually on that large scale track. Later on, we built a classroom version. I think the initial larger track was something on the order of 50 by 60 feet. This one's actually much smaller, 16 by 20 feet. Suitable for classroom use and can be constructed for less than about $25. Here's, I'll just show just a very brief video of the system that was developed in use in autopilot mode, that is, it's self-driving. And as you can see, there's yep, there it goes, navigating its way around the course, around the cones that may represent a pothole or a pedestrian. Simultaneous real-time visualization is occurring as well, so we can see when we set it up with the TV, that happening and see what the camera sees in real time, which is very exciting. So right now it's just driving on its own, and so this is what it's capable of doing as a starting point. Moving on to task 4. With this, we didn't just develop a tool, but learning activities and associated lesson plans as well. So the developed activities and lessons emphasize problem solving, peer learning, teamwork, research, reporting, and technical writing. And they encourage laboratory experiences ideal for self-discovery and creativity. Again, we wanted to hit on that first priority standard of persevering in problem solving. So there's a lot of self-discovery kind of on the order, which is really, really at the heart of STEM education. So we've, there's a number of different lesson plans associated with the system as well. We'll talk about some of those in a little bit. Along with our lesson plans are resources that were developed for this task, that developed in this task 5, and they're intended to be used by educators to supplement or diversify their existing STEM integrated curriculum. Specific to the scaled CAV system, these supplemental resources include process documentation, assembly instructions, discussion ideas, and related educational content. And again, we've done this in collaboration with educators, adding, discussions, adding resources based upon their needs as we get feedback from them. And a lot of that occurred, during our survey, but much of it occurred during the learning experiences of our classroom outreach, which we'll talk about in a little while as well. Our ENG2YOU Educational Resources, I'm just giving one example here. This is test track construction and pavement marking evaluation project. So in this project, students, the project summary reads as follows. In this project, engineering design teams will construct a set of test tracks for a scaled machine vision based, that is camera based, connected autonomous vehicle using different striping materials, that is pavement marking tapes, and evaluate the visibility, retroreflectivity, and general usefulness of each under various lighting conditions. So this is really our students entering into the exciting world of research. From this, the student engineers, they're able to practice reading schematic drawings. They're able to review imperial and metric systems of measurement. They're able to consider important variables and controls. They're able to establish means and standards of evaluation and testing, again, persevering in problem solving. They're able to learn, obviously, about connected autonomous vehicles and the associated smart infrastructure that they themselves were building. They were able to discover the advantages and limitations of camera sensors. They were able to experience the engineering design process and enter into it fully and discuss engineering team dynamics. Everything they did was on a team. So we've used this in the classrooms. There's just one example of an educational resource that an educator can use for, in this case, probably most suitable for about a 2-week project. Again, aligned with, all of these Ohio learning standards. It can fit nicely in, in a high school curriculum. Here's a few pictures of when we actually put this into practice, the materials that were required for this project, in which they're building 2 different types of infrastructure kits and then testing with our scaled CAV system, the retro reflectivity of the different pavement markings. All of this was purchased for under $50. Here's our students. This is at Aiken High School. This is a Cincinnati public school, slightly on the west side of Cincinnati. Here's our students in action. I love this. I love the collaboration that's taking place in this picture, right? I love the problem solving that's taking place. So there's not a lot of hand holding that's going on here. They really had to enter into it, to discover for themselves and persevere in problem solving in that way. And the results were very exciting. There's much I could say about that, and maybe we'll share a little bit more when we get to our Q&A time. In task 6, we also wanted to empower our Ohio educators via training. First, and we did this in a number of ways. First, the research team hosted a series of online connected autonomous vehicle education open house, virtual open house events. These were really our early adopters from the feedback that we were getting from our survey. So, all of these relationships, we're still in contact with these educators to this day, and all of them are in one way either using or very interested in the system and the associated resources that we built. Here's a few pictures from those webinars, that training. STEM educator outreach. The second, the research team presented to this project a CAVE specific project option to 8 new college credit plus instructors representing 8 local high schools during their summer training at the University of Cincinnati. We also had the opportunity at the ENG2YOU Future Engineers Camp to offer parallel training to chaperoning educators aimed to empower them on the topic of connected and autonomous vehicle technology using our own resources. In task 7, we hosted an engineering leaders training for 2 days in the summer of 2023. We were able to, now the undergraduate ENG2YOU leaders that were trained by us, some of it was leadership training. The other part of it was training as they would serve as coaches for our young participants during the ENG2YOU camp that would be the subsequent week, the following week. So we walked through our ENG2YOU camp schedule. We did a live demo of CAVE project applications. We reviewed the embedded technologies, and this was new for them as well, right? So we wanted them to become the experts so they could be the first line of defense in any questions that our middle school and high school campers would have. We also discussed a lot about team dynamics, with the aim to be to encourage, and to make sure that our ENG2YOU participants were having a lot of fun. So here's just a few marketing materials from our summer programming. First, our engineering leaders training, and then moving into our ENG2YOU Future Engineers Camp, which I'll talk about now. During a 4-day camp from July 25th through the 28th in 2023, the total number of attending students, about 40. We were really pleased with that number. Truth be told, we had over 125 that had applied, and we selected 40 for a variety of reasons. Probably the top means of selection was STEM educator reference, particularly if they were referred by an educator that we had an existing relationship with that we felt was kind of a long-term play to really engage in that school, with that teacher, with that young person in the months and the year ahead. The total number of trained undergraduate coaches for our ENG2YOU training the week before was 6. Here's just a few pictures of, this was just a huge logistical effort, and I can't possibly stress that enough. So in addition to, developing a learning tool and activities and high energy camp for, 40 middle school and high school students over the course of a 4-day period, things like parent communication, things like the medical releases, the liability waivers, things like the reservation of space and materials and food during lunch. So here's our camp handbook, where we really try to help our parents out as much as possible, and the feedback that we got was really extraordinary from both the students and parents alike. Here's an outline of our schedule. Really, day 1, connect, day 2, learn, day 3, explore, day 4, lead. Really kind of entering into the path of what a connected and autonomous vehicle is able to do. It gets connected, is able to learn something new. It explores based upon the information that it's received in the past. It's able to lead others, or maybe be connected to another vehicle, right? So we kind of allowed connected and autonomous vehicle education to penetrate even our schedule and the themes for the day. We had an amazing lineup of speakers, tours at the Digital Futures facility, and this was all part of this project. So, it wasn't like we were coming in and speaking at a camp. We made a camp, which is, we're very proud of this. A few pictures of our time together over the course of those 4 days. And I may not show this entire video, but just to give you a sense of what this was like, you see our track set up. We had actually 8 student groups, 8 kits where they were able to build, design, and actually sketch out the design of their own connected autonomous vehicles, design it from an engineering perspective, design it from a kind of an artistic, aesthetic perspective as well, and then they really, so here they are jumping into that process. But after they would design their system, construct their system, they would go through the effort of collecting data on our track. You can see some of the schematics that are outlined here, lots of different Lego activities and team building exercises and icebreakers, just a lot of life, a lot of energy in that room over the course of that 4-day period. And we'll have the opportunity to share some of that student feedback and parent feedback when we talk about the results of this project in just a little bit. We actually had Leidos, who had developed Cave in a Box, actually come out and bring Cave in a Box, the original inspiration for this project from the outset, come in, share a little bit with our students as well. So we're grateful for their participation and ongoing support and what it is that we were trying to do. Truth be told, so after they collected data, they processed that data, visualized it, cleaned it. Each group, we had 8 groups in total that were assigned to a laptop, and then after training that data, they would have ready to go their scaled, connected, and autonomous vehicle system. And then at the final day of camp, we raced our systems. It was actually came down to a photo finish at the very end. So this is our last day of camp, highlighting leadership. Dr. Munir Nazzal, Michael Backers. We had a number of industry and academic leaders that were able to come in and talk about their discipline, their specific discipline of engineering, and ultimately inspire, right? Which is our goal to tomorrow's engineering leaders. So here's a few, our group together. And here's the winning team. They all were awarded with their first place trophies. It came down to a photo finish. So just a very cool, fun 4 days. And I think everybody was looking forward to doing it again in the future. In task 9, the research team organized student outreach events throughout Southwest Ohio, namely Reading Juniors Senior High School, Finneytown Secondary Campus, and Stebbins High School were our principal locations for this. We had great relationships with Scott Drasowich at Stebbins, Ben Kolb at Reading, Mr. Phil Farr at Finneytown. So we really, capitalize on those relationships, and we're able to spend a lot of time in those classrooms and perfect and improve upon our resources and our system as a result. So relying on developed lesson plans, tried content from the ENG2YOU Future Engineers Camp, and the unique opportunity to meet an engineer, these student outreach events operate as a kind of mobile laboratory consisting of interactive demonstrations and inspirational lessons. Beyond the educational experience provided to the students, these events also invite opportunity for ongoing feedback and improvement to the package of tools and resources, which was important for us as well. I'll just highlight a few, certainly not all of them, but we're able to visit for an extended period of time Finneytown Secondary Campus on February 9th. This was part of an awards presentation. So as part of our ENG2YOU camp, we invited our students to take us up on what we called a take-home challenge, in which we offered them a project. There was a middle school version and a high school version, and there was a certain deadline that was associated with that. I won't go into too many of the details, but DeMarco Bryant took us up on our challenge, wrote a very impressive proposal highlighting how he would use light detection and ranging, LiDAR, to improve upon our scaled, connected, and autonomous vehicle system. So this was also an opportunity for not only to engage and the students of Finneytown to teach on connected and autonomous vehicle education, but also to award DeMarco for his work, his research, which was very exciting as well. So here's us in the classroom. This is us awarding DeMarco. At Reading Senior High School, our resources have actually become the foundation of an after-school engineering club that meets the second Wednesday of every month. These are students that we have long-standing relationships with because we're spending at least a month with them. So we know them by name. There's Blake and Jordan and Gio and Seth and Jackson. This is also, so Ben Kolb is actually hired through Great Oaks to teach engineering. He teaches an introduction to engineering design course, as well as an automation and robotics course. And so some of our resources fit nicely into the curriculum that's been established by Great Oaks. Their opinion on the matter is this is exactly what you should be doing. So here's us in action at our after school ENG2YOU club, right? So everything is under that banner, that moniker of ENG2YOU, where we want to bring engineering, make a connection between engineering, the big, bad, scary world of potentially something I may be interested, but seems a little bit distant in the future, to you, to the average high school, middle school student, right? That's the logic there. And then finally, we prepared and submitted a final summary report that was actually submitted this morning. Here's an example of our fact sheet as well that was included with our summary report. So with the time that we have left, we'll spend about 12 minutes or so, make about 10 minutes for question and answer. Really want to hit on the results, okay? And some of these are numerical. Some of them are experiential results too. Both from our perspective are quite important. So let me just begin with a few student comments from our ENG2YOU camp. Here's Maria Timmers, Jr. She says, I knew almost nothing about caves beforehand, and now I can talk about it forever. It's so cool. I love that. Lily Jones, a freshman, she says, I learned a lot about AI and some new types of engineering, as well as a lot of what goes into it. Luis Santos, a senior, was quoted as saying, I learned how to continue going through hardships and difficulties. So yes, there it is, like that first priority standard of persevering through problem solving, like that, that amazing Ohio learning objective, mission accomplished. Some other great statements, one from Jack Polger. I learned that there are many careers stemming from all types of engineering. Learned lots about material science and the methods of collecting data. I also learned about the future of autonomous vehicles and how they are already implemented. Addie Lange, a freshman, says, I learned LiDAR and learned about different roles on an engineering team. That's fantastic. Mahi Jasti, a freshman, was quoted as saying, I learned how automated vehicles worked and how much of an impact they will make. So our summative assessments will get down to the actual numbers themselves after ENG2YOU. So this is data that's specific to our engineering camp. And I'm leading with this because really this to date has been our most comprehensive use of our scaled CAV system, the tool, as well as the resources that we built out. So this is really the project in context. That's the way that I think of it. So our summative assessment after ENG2YOU, 0% of attending students identify themselves as being unfamiliar with connected and or automated vehicles, down from 34%. 37% of attending students identified themselves as being somewhat familiar with connected and or autonomous vehicles. 63% of attending students identified themselves as being very familiar with connected and or autonomous vehicles, up from 4% at the start of our camp. So we went from 4% to 63% in the course of a 4-day period. 13% of attending students, when describing their knowledge of connected and or automated vehicles, selected, I've heard of them before, but I'm not sure what they do or how they work, down from 69%. Continuing with our summative assessment, 97% of attending students identified themselves as considering a career in engineering, up from 77%, which makes sense. This is an engineering camp after all. So there is some initial interest in engineering, which makes sense. But now we're up to 97%. Here's the real kicker. 67% of attending students identified themselves as considering a career in transportation, not just engineering, up from 7%. Now 67% think, hey, this might be something that I want to investigate as a future career path. That's excellent. 56% of attending students recorded that ENG2YOU reinforced their goal to become an engineer. I was very pleased with that. So the following table summarizes the percentage of attending students who had previously identified themselves as being unfamiliar with the associated terms, words before ENG2YOU, but identified at least some degree of familiarity after the camp. And so words like infrastructure or V2V or what a Raspberry Pi is or what a variable is. Obviously, we have a vocabulary that's very broad here. Some of these questions are appealing to the middle school students that were in attendance, some to the high school students that were in attendance. But things like, V2V or V2I or V2X, over 80% improvement in, understanding what it is that that we mean by these terms, by these words. The parent feedback. So about a week after the camp, we sought after the feedback of our parents and just asking them, a few important questions to see what the lasting impact of the camp would be. Our first question was, if still age eligible, would your son or daughter be interested in attending the proposed 2024 camp? 86% said yes. Would you recommend the ENG2YOU Future Engineers Camp to another parent, age-eligible family member, or to a son or daughter's teacher, classmate, or friend? 93% said yes to that question as well. And then we kind of invited some of those experiential comments as well, that experiential data. Please describe any signs of lasting impact or enthusiasm for engineering shown by your son or daughter following the 2023 ENG2YOU Future Engineers Camp. How often it is you go to a camp, you have a great time, you come back home, get in the routine of things, and you kind of forget about what it is that you learned, the experience that you had a week or two prior. Here's some of the feedback we got. Impacting with the cars and moving forward in the future technologies. I hope he has the opportunity to go again next year. My son starts to show interest on drone courses and AI interaction. Jeremiah has been amped up to build things and considers how things function and are maintained. Jack joined JETS, which is, I learned kind of an engineering club at his high school. Another comment, she still talks about the things she learned that week. And then finally, my daughter really enjoyed the camp and helped her decide this is really what she wants to do. At Finneytown, just some of the student feedback here. We had 37 students participate in our pre and post assessments. So, again, like that summative assessment, that pre-assessment, when we, before our visit, 47% of participating students reported that they were not yet familiar with connected and autonomous vehicles. 39% were quoted as saying, I've heard of them before, but I'm not sure what they do or how they work. At the end of our visit, the following percentage of participating students identified to be at least somewhat familiar with the following terms increase. So, an increase of 49%, for the term infrastructure, 49% for LiDAR, 41% for machine vision. Notably, at the end of our visit, 4 participating students out of the 37 that participated reported they were now considering a career in engineering. 2 participating students reported they were now considering a career in transportation. I'll take that. And then one more classroom outreach that will highlight the results of Stebbins High School. We had several visits to this particular high school campus. In our final visit with our freshmen and sophomores, 42 students participated in our pre-assessment. 36% of those participating freshmen and sophomores reported, again, not yet familiar with connected and autonomous vehicles. 48% saying, I've heard of them before, but I'm not sure what they do or how they work. At the end of our visit, here's those same terms again, or several like it: infrastructure, LiDAR, machine vision, the increase in knowledge and familiarity with these terms. And again, at the end of our visit, 8 participating freshmen and sophomores reported they were now considering a career in engineering. 6 participating freshmen and sophomores reported that they were now considering a career in transportation. For the juniors and seniors, we had 39 student participants, 8%, just 8% says not yet familiar with connected autonomous vehicles. 21% noted as being familiar with them or hearing of them before, but not sure of what they do or how they work. At the end of our visit, 97% of participating students and seniors correctly answered temperature when asked which of the following is not a type of data collected by the scaled CAV system. At the end of our visit, 92% of participating students and seniors correctly answered friction of the track surface when asked, considering the limitations of its camera, which of the following is not an important variable when the scaled CAV system is driving autonomously. And then most significantly, at the end of our visit, no participating students, however, report they were now considering a career in engineering. This was an engineering class at all, so maybe they were before, but we didn't really move the dial in that regard. However, 6 participating juniors and seniors reported they were now considering a career in transportation. One such student is a student by the name of Brody Simila. He's quoted here, "This was very educational, loved the energy and enthusiasm, great job." He's actually coming to UC this fall. We visited him kind of a number of times during his visits to campus, had a great relationship with him, and he actually cites this ENG2YOU program, beginning with the camp, as well as the classroom outreach events, as being the principal inspiration and motivation for him to pursue a career path in engineering, which we love to hear. Most significantly, at Stebbins High School, at the end of our visit, 100% of participating juniors and seniors reported that they thought that the scaled CAVE system is a fun tool to help students learn about connected and autonomous vehicles. That was the goal of this project. When asked about the use of the scaled CAVE system as an educational tool, 2 students also recommended, and we love this feedback, that we talk and teach more about the associated code. So again, another opportunity for us to build this out further in the future. This was very good and educative. Again, Brody, very educational. Love the energy and enthusiasm. Great job. At Aiken High School, similar comments. It was cool and different, says Alexis. Destiny says, fun program. Ryan says, it was cool. So 8th graders, sophomores, freshmen, all getting behind this, participating, and enjoying themselves along the way. Finally, just a few conclusions and recommendations before we, make some time for questions and answers. First of all, formative assessments, educator collaborations, and parent feedback have demonstrated the developed scaled CAVE system and those learning opportunities in which the system has been used to be effective educational resources. Number 2, further research is needed to explore the complementary use of LiDAR. Some of that was done in the course of this project. Much more could be done in the future. To build out additional object detection algorithms by which new application scenarios may be created, and to perform a cost-benefit analysis of compatible camera sensors by which the reliability of the system may be improved upon without becoming cost prohibitive to our target user populations and districts. Prior to each use of the scaled CAVE system, the research team recommends that the available internet connection, classroom lighting conditions, and battery life of the car, power bank, and controllers be considered and tested. But even in the course of failure, there's no failure, because even these are opportunities for the students to persevere in that problem solving and to understand what could be improved upon with respect to environmental scenarios such as lighting conditions and internet connections and things like that. So even those, can be opportunities for learning in the classroom. Additionally, outdoor use of the scaled CAVE system at this point is now recommended, and users are caution to avoid reckless driving during data collection. The reason being that the small board computer, the Raspberry Pi, could potentially overheat under those scenarios. Finally, and I really want to underline this as well, the research team recommends further research be ordered to the development of non-degree certification programs specific to CAVE education and targeted to high school students interested in pursuing such certification. I really believe that this is where a lot of opportunity still exists, and potentially a way to extend this project and this research further into the future. With that, I'm going to pause for questions. If anybody has, I'll be sure to check my comments as well to see if anybody has included questions.
All right. Thanks, Ryan.
Yes.
Yeah.
Thank you, Mike.
You're welcome. As a reminder to our audience, the questions box is available in the GoToWebinar panel, so please feel free to type in any questions you have, and I'll mention at the very start of the broadcast there was a question as to whether this would be recorded, and the answer is yes. We do record all of our webinars, including the research results presentations. So later this afternoon, we'll be posting a video recording of this webinar broadcast to our Ohio LTAP YouTube channel, and then we'll send out a follow-up link to all of the participants with that video link included. So we're glad to share that resource. As we're waiting for additional questions, let me mention we also have Vicki Fout on the webinar today. And Vicki is with ODOT's research section. She's familiar with this session, as well as earlier today, there was a research results webinar on a related research to this project. So Vicki, if you're there, you're welcome to share any comments you might have. Okay, no word yet. Ryan, as we're waiting for additional questions, any other information you'd like to share about this project?
I'd also like to highlight that the resources that represent the deliverables of this project will be included both as part of the 2024-2025 Drive Ohio Educator Toolkit. So you'll be able to find them there if anybody is interested to links to that toolkit. That's something that we could provide to you in the future. They'll also find a home on the University of Cincinnati's workforce development page for the Center for Smart, Sustainable, and Resilient Infrastructure, CSSRI. And this will be, things that we continue to build out. So with that, you'll find some of our existing lessons, which may either be kind of like a 1 to 2 day lesson, a 3-week unit, or or all the way up to semester-long projects. And of course, educators can get creative on how they intend to include that as well. You'll also be able to find a parts list of what is needed for these various assignments, most specifically the scaled CAV system itself, and some process documentation on how to construct it, program or reprogram accordingly, and things of that nature.
Thanks, Ryan. We have a question submitted, which is, how do we purchase the Cave-in-a-Box materials and resources?
Yeah, so some of the resources may be found by so as a starting point, we used a system called Donkey Car. And so some of those resources can be purchased on their site. Kind of going along with my statement from just a minute ago, the reference parts list will include all of the different parts and features for what is needed and what may be purchased in order to actually build the scaled CAVE system. So some of that will be found on the Donkey Car website. The majority of it can be purchased online via Amazon. So for instance, the Raspberry Pi, generally for less than $70 on Amazon. Same with the Google Coral AI processor, the power bank. These are things that you can find on Amazon, and we'll be sure to kind of include the full package of everything that's needed as part of that parts list. And you'll be able to find that beginning this fall, likely as early as September of 2024.
All right, thanks, Ryan. There's a question. I'm not sure of the wording. Will you be able to provide training on how to construct the curriculum, or maybe they meant to say instruct the curriculum?
Absolutely, yeah. So some of that training has been recorded, but I think probably the best way, and we love to do this, this is something that we're very passionate about at the Center for Smart, Sustainable, and Resilient Infrastructure. If there's an opportunity for us to visit a classroom or to provide training for any particular audience, and usually what that audience is either an audience of young persons, but it could also be an audience of educators. We're happy to provide those trainings. You'll also be able to find my email address on both the CSSRI workforce development page. It may also be included as part of this project as well. It will be included as part of the Drive Ohio Educator Toolkit. So anybody can reach out to me, and either I can supply, depending upon the type of training that's desired, either supply a video reference that might be able to satisfy that need, or, you know, maybe it would be my preference as well, because we do enjoy doing it so much, actually visiting that school, visiting that classroom, or visiting that audience and doing some on-site training with the educators or whoever the audience may be. So some of it is recorded, and some of that training you'll be able to see. But if it's always kind of better for those things to be interactive as well, and so we're happy to make time and to make ourselves available, and especially if it's within Southwest Ohio, or someplace that's particularly local to the University of Cincinnati. Yeah.
All right, thanks, Ryan. Our timing is very good as we are reaching the 1 hour mark. So let me just mention we have many upcoming webinars and training courses available through the Ohio LTAP Center here at ODOT. So please feel free to visit our LTAP website, our available training webpage with upcoming sessions listed. Also, please feel free to visit ODOT's research section website for additional information and resources. So with that, thanks everybody for your participation today. And Ryan, thanks so much for sharing this information. We really appreciate it.
Thank you, Mike, and thank you for all those who participated, offered questions, and hung in there for this webinar. I'm grateful.
Thanks, everybody. Bye.
Take care.